In fact, the entire unit on features. This kind of work, finding features, figuring out how they match, is pervasive in sort of geometric computer vision, the computer vision that talks all about how cameras align and scenes and depths and points. And so they used a lot these days because of just how ubiquitous imagery and video is. And because these methods are sort of powerful and real, and not just math, they're used in lots of real applications. So I expect if you end up doing any work that involves dealing with multiple images and trying to figure out something about the relation between them, that you will actually see things like Harris detectors, things like the SIFT descriptors, and certainly things like the ransack alignment. All right, welcome back to Computer Vision. Today and the next couple lessons, we're going to spend just a little bit of time on sort of the whole light reflection process that results in photons essentially hitting our camera or our retina. The idea that this is how the physics of the imaging or the creation of the light that the imaging is going to make a picture of. And there's actually a huge amount known about this area, and it all comes from both sort of the material science, where we study the materials, but the big motivator has been computer graphics, right? Computer graphics, the idea is I have some model of an object and its surface type, and I have some model of the light, and I'd like to produce an image as if you were actually looking at the real object. So to do that, I have to understand how light interacts with these objects. Now, in the old days, and when I say the old days, I mean like 20 to 40 years ago, there was this view that computer vision was just inverse computer graphics, right? I mean, computer graphics, you have a model of the object and a model of the light, and you make a picture. And computer vision was thought of as, well, given a picture, can you tell me about the light and the object that's there? And so there was a lot of focus on recovering image surface properties and object properties and lighting conditions as sort of an inverse problem. And to do that, we had to have a lot of understanding of the physics of how images were formed. Now, more recently in computer vision, a lot of what we talked about here, there's been more of a focus on really the geometry of sort of where features get located, and that relates to sort of the shapes of objects and the relation. And you didn't have to worry quite so much about the precise physics. And then also a lot was saying, let's lump all together the lighting, the shape, the texture, the imaging, the camera, etc. We just get out pictures, and we use machine learning or recognition techniques to try to do labeling. And we talked, and when we will actually be talking about that in the future. But it's still important to understand something about how the physics of light works with respect to making images. So here's a sort of toy or a schematic, right? So the general idea is that we've got some lighting, all right, and the lighting hits objects. And so we need physical models or models of the physics. And the idea is that that causes light to impinge upon whatever your photosensitive system is, whether it's a retina or a CCD or CMOS or whatever your imaging technology is. And then, of course, that's the picture that we're going to take a look at in the computer. So there are all sorts of physical processes that impact the image that you're going to see. So, you know, here's a picture. I think actually this might be from Mark Polyfe's. Don't remember. You know, here's a picture, two pictures, and it's pretty clear to you what's going on here, right? That we've got this sort of textured stuff everywhere, and that there's differential light falling on it, right? That there are these shadows. And so when you look at that, you probably don't think that that's a texture painted on the surface of the road, but rather that that's a shadow on a more uniform texture. But of course it could have been painted, so your brain has to be doing something in order to understand that. And this white tape that's shown here is just a little bit showing you sort of how things appear to you, right? To you it's clear that this is a thing that's on the ground, right, that is not part of the texture of the ground, but is something else. So you've said, okay, that's one thing that's reflecting one way, and I've got some other object, namely the asphalt, that's reflecting another way. So that's sort of lighting surfaces and shadows. Of course, there are reflections, right? So in both of these window pictures, you know, you're probably guessing that there's not like this thing here that's behind the window, and maybe it's just a reflection of what's behind you. Likewise, you can see in this tree, it's all distorted a little bit because maybe this glass isn't so perfect, but the idea is that you can see this reflection, and that reflection is impacting the image that gets made. Going along with reflection is refraction. right? So it's most easily seen in things like water or various kinds of deformed glass. So here, these wavy lines on the bottom of the pool, well, there are no wavy lines on the bottom of the pool, at least I hope not, but instead the water itself is no longer flat there. There are some waves, and that's causing the light rays to bend in a particular way. So again, that impacts the image that you see. This beautiful picture here has got both reflection and refraction going on inside of it. An interesting property, which is really, it's just about reflection, is what's referred to as interreflections. And both of these pictures are drawn from computer graphics. It's not so much about the nature of the surface, but what impacts the light that you see at a point. And sometimes we tend to think of, well, there's just some light source and it's illuminating our objects. Well, there's been a lot of work done sort of since the 90s on what's referred to as interreflection, both in computer vision and computer graphics. So here when we have these shiny materials, you can see everything being reflected within it. But I think a more subtle example is, this is the famous graphics teapot being rendered in a variety of ways. Now, of course, in a shiny surface, you know that you're going to see a reflection of this purple teapot in front of it. But also in these partially reflective things, you see this purple color in there that's reflective of this purple pot that's in front of it. So the idea is you have all this light bouncing around, and all of that light can impact what's actually observed at a particular point. In computer graphics, there's a method called ray tracing, which basically, as rays of light come in and they bounce off, they create illumination at all these different facets of the model, and you can get a really rich rendering. One of the things that's a little different in computer vision today than before is, traditionally when I taught computer vision, I could assume that everybody had taken graphics, because there was sort of this connection between graphics and vision. These days, it's much more likely people will have taken machine learning, because there's a view of computer vision as a data-driven inference problem, and people are less likely to have taken a graphics course and understand the physics that are here. Computer vision draws both from understanding what's going on from data, but also having built-in models that have to do with the nature of the physics. Then there's things that happen to the light between bouncing off a surface and entering your eye. So here's an example referred to as scattering, where this is what the picture maybe should look like if you think of it as being very clear. But if you actually just took a look at the raw image, you would see this because of moisture and other particulates in the air and the wavelengths that are absorbed, that the light changes as it comes through. And in fact, there was a really cool paper done about depth from what's called the dark channel, which basically says that the further away something is, the harder it is for something to be black in your image, because there's a little bit of fog all the way through. So they actually estimate the depth of the scene based upon essentially the amount of fog-induced lightness that's there. And this is all from an understanding of the nature of the physics. And there are lots of other phenomena that impact, the light that comes in. Here's fog and water dripping and all sorts of different types of effects. So what we're going to talk about today is essentially the surface appearance of objects. And what we mean by that is, the question is, if I've got some surface element and it's being illuminated by a source, what is it that the sensor is going to see? And the idea is that the image intensity is going to be a function of a couple of things. One is the local shape, and we can think of the shape as just being the surface normal of a little patch. Then there is the surface reflectance, that is, what are the properties of the surface that affect the light. And then there is the illumination, that is both the direction and the type of light that's coming in, sort of its intensity, maybe its wavelengths, and those kinds of things. And the amount of reflection that will be observed is a function of both sort of the incoming direction and the outgoing direction and its relationship to the surface. And we're going to make that a little bit more formal going forward. So now we're going to do just a tiny bit of nomenclature with respect to the physics. It's a little bit confusing, and later we'll drop some of it, but it's important to get just a little bit of a basis. So the general area of considering light is sometimes referred to as radiometry, which is the idea of measurement of light. And the first term that we talk about is the radiance, okay? So the radiance is always some light that is being carried by a ray, or sort of, you can think of coming off of something or out of something. In a minute, we're going to talk about the irradiance, which is the amount of light falling on something. All right. So the radiance is sort of energy, as it says, is energy carried by a ray. And what I want you to do think about is assume there's like this little patch out here that's of a sort of a fixed angle that's observed down here at some point. And this angle, this little patch we'll call d omega. All right. So radiance is measured as power, the amount of energy per unit area. But the area is measured perpendicular to the source. So if this is our little area here, okay, but our light source is over here, we'll make our little sun there, okay, and this is a little patch of the sun. What we actually have to think about is the area perpendicular to that ray. And so because it's perpendicular, we measure, this is going to be a little weird, we measure the amount of radiance in this funny unit called watts per square meter. So that part's okay, right? It's watts per, you can imagine watts per square meter of that little disk, but it's per what's called steradian. What's a well, you know what a radian is, right? A radian is a measure of angle. A steradian is a measure of solid angle, right? So this is this little cone, this is a cone funneled out, right? And the steradian is the amount of angular area of that cone, okay? Because if I had some big sort of extended source here, you'd have to integrate over all of this different area, but we're only going to use this little delta omega patch. And like I said, in a minute we'll simplify this whole thing. But just this idea is that the energy that's coming from that thing is a function of, so I have to think about how much light is falling on my area as a function of the amount of different area that I can see up there, right? So one is the area down here, and the other is the amount of the source that I can see, and that's measured in steradians because it's the solid angle. The irradiance, sometimes called energy E, that's the energy actually arriving at the surface. Okay, so now we're going to talk about the energy at the surface. Okay, so now I've gone back to, and I'm going to leave both this perpendicular part and this is the area on my surface. Okay? Now, it's because I'm actually looking at my surface, I'm just going to measure that as the power per unit area, so that's just watts per meter squared. Okay? So clearly, there's this relationship between the amount of energy hitting that perpendicular part and then this skewed, the area on the surface. And the easiest way to think about that is to think about this as a foreshortening effect. All right? So here we have a light source. And the idea is that this is the direction of light, and this area, this card here is meant to be perpendicular, right? So there'll be a certain amount of light falling on that card, right? But if the card was not perpendicular, right? If the card was tilted away, then the same amount of light now gets spread over a larger area. And so it's foreshortened. So in other words, we get less light per little unit area from that light source. And we can write that down in the following way, sort of for a surface receiving some radiance from some direction, coming from this, we'll say, fixed little patch d omega. The corresponding irradiance, the light landing on the surface, is just the radiance modulated by this angle, right? So as that angle gets closer and closer and closer to pi over 2, 90 degrees, the amount of irradiance goes down to 0, which is right because you're essentially spreading the same amount of light over a much bigger area. So that sort of talks about the energy, and now what we have to do is we have to talk about what is the relationship between the light coming in and the light going out, because the light going out is the light that's going to go into your sensor, all right? And to model that, we use what's called the bidirectional reflectance distribution function, or BRDF, okay? And the idea of the BRDF is that I've got a little surface patch that has a normal, and my light comes in at some angle, and I'm going to be viewing it at some other angle, all right? And I want to talk about the amount of sort of the proportion of this light that comes in as sort of what proportion of this light coming in this direction goes out in some other particular direction. By the way, this angle theta here, that's the tilt angle. That is the amount that you're off of the normal. And then there's a rotation around the normal. That's the phi, okay? And for some surfaces, we actually have to worry about both of those angles, all right? And so the irradiance is the amount, just as we said before, it's the light per unit area that's coming onto the surface. And now It's radiance because now it's not the radiance from the light source, it's the radiance back from the reflecting surface. Okay, remember, radiance is the stuff coming out, irradiance is the stuff landing on it. So now we have this, before the radiance was the stuff coming out of the light source.